Anyhow, this is the joy of the learning experience. You have stuff. What do we use our differential equations for? Well, I want to use them for models. I want the differential equation that creates a mathematical description of something that is happening, some phenomenon, some system of events. And there are really two steps in creating this. The first is to identify all of the variables. What's important to understand the things that make changes in the system? Now, this is sometimes referred to as the resolution. Identify, right? Identify the variables. Idea. Tell me what the variables are that we need to know about. This is called the resolution, i.e., more variables, higher resolution, fewer variables, lower resolution. And then we figure out what's a reasonable assumption about how those things behave. And the roles of the variables within those. So if we've got empirical laws, when we make assumptions about physical objects, I would like to use the rules of physics. So I'm going to use things like gravity, acceleration. I'll use things like forces. If I have those sorts of things. If I don't have that, I may do some experiments to try and deduce what's going on. If I can get some basic idea of what's going on, I can then say, oh, this changes in accordance with its relationship to, and I can write a differential equation. Sometimes it's more than one, and I write a system of differential equations. Sometimes it doesn't just involve first orders, and I write a higher order differential equation. So it's going to depend on what's happening. You've seen this before. I know what's going on now, and I know that every so often a change occurs. In linear, we did this with Markov processes. I had a matrix that measured the change in state. That's exactly the same idea here. I'm trying to figure out how to get a relationship between what's going on now and the changes that are going to result because of that. Now, once I've done all of this, I'll try and solve the differential equation, if I can. If there's a system, I'll try and solve the system. Our solution is called the state of the system. Bottom of page 22, little picture. I make some assumptions and hypotheses. I write them into differential equations. That's my mathematical formulation. I solve that. I get a solution. Let's look at what that solution is. Maybe I'll make some graphs. I'll draw some pictures. We'll figure it out. And then I'll check it against the way the real thing operates. If I get it right, I get it wrong, I can go back and change, add some more variables, take some away, change the assumptions, and then I can roll through this circle again and again and again. This is the overall process by which we do modeling in mathematics. Questions? Then let's start with a nice, easy one. Here's an example to work off of. Population growth. All right, let's make some assumptions. I have a population of things. We do bacteria, people, cats, birds, mice, whatever, it doesn't matter. Things. How do I determine the change in the number of things in my population? It's going to depend on how many there are, right? If there are a lot of them, maybe they breed frequently, maybe they breed infrequently, but if I have a lot of them, I should expect bigger growth than if I have a very few of them. Yes? And if my population is growing, then there should be some relationship between the derivative and the population that's positive. So I could say, if P of t is the population of whatever at time t, then I could say that the change in population is proportional to the population itself. Big populations have bigger changes than small populations. We will often see this phrase replaced by an alpha being used like an equals sign. So if the population itself is P of t, we can see this written like this. The change in the population is proportional to. Personally, that symbol drives me nuts because I think of alpha as a constant, and that bugs me. But it's a very particular alpha. It's a very special symbol. I believe it's in the textbook on page 23. It's a funky looking alpha. But really what that means is that there's some constant in there. This is unbounded growth. You have a petri dish with a bacterial colony in it, and the number of bacteria doubles every hour. T is in hours, then K would be 2. This differential equation for population growth was really first brought up in the 1700s, I believe it's 1798, a guy by the name of T.R. Malthus. He wrote a paper about human population and the speed with which the population was growing. And he claimed, Malthus said, that the population of human beings on the planet would at some point in the near future grow faster than our ability to grow food to feed them. I found the original paper in my copy of Newman's World of Mathematics from the readings course last year, and I stuck it up on our Canvas page. It's not a very long excerpt. It's only 5-6 pages, but it's a very interesting read to me. If you're interested in where this first started to show up, that paper's on Canvas for us. Every time somebody has predicted a Malthus-style collapse, population outgrows our ability to support it, we've invented new stuff. We invented new methods of farming, and all of a sudden our ability to feed ourselves jumped quite a bit. We developed hydroponics. We developed desalinization. We got better water. All of these things changed, and Malthus has been wrong repeatedly. In the late 70s, a guy by the name of Paul Ehrlich wrote a book called The Population Bomb, in which he basically reiterated Malthus's idea. And he said, we're going to grow so fast, the population of the Earth is going to be bigger than 6 billion. We're never going to support that. The entire Earth, the ecosystem is going to collapse. It's the population of the world right now. Almost 7.5, 8 billion. Yeah, he was wrong. Surprise. But this assumes we continue growing forever. Is that reasonable? Population of bacteria in my petri dish doubles every hour. What eventually happens? Cody, you were shaking your head. It gets full. I run out of space. I don't do a lot of growing of bacteria in petri dishes, but the growth medium, the jello that they grow the bacteria on, contains a finite amount of nutrients, and you've got a finite amount of room. At some point, the system won't support continued unbounded growth. So this is a very simple model, but it's not a very accurate model. It's not high enough resolution. There's more stuff going on here that I would need to take into account. All I've taken into account is how many births happen every time period. So I know this is a nice, easy model, but it isn't 100% accurate. I don't remember if I told you guys this story, and if I think I told it in this room, but I don't remember which class I was telling it to. I thought I had a heart attack. Doctor sends me, says, we're going to give you a cardiac stress test. And they hook me up to an EKG, they make me walk on a treadmill. And both before and after the exercise, they take pictures of my heart. How do you take pictures of a muscle? What's a CT? CT is an X-ray. Computerized axial tomography is an X-ray machine. X-rays go through muscles. Yes, they use a CT, but in order to see the blood vessels and my heart, they inject me with a contrast medium. The contrast medium is technetium-99. So they pull out this syringe that looks like it came right out of the Wolverine movie because it's full of this silver metal. They stick it in the IV and shove it into my arm. And I'm a little disturbed by this until the guy says to me, technetium-99 is a radioactive isotope. We'll be able to see it on the X-ray, and then it will decay from its radioactive state to its non-radioactive state. So we'll take the pictures now, then we'll put you on the treadmill, and then we'll put you back in the CT machine and take some more pictures, and we'll be able to do it before and after. Your heart will be pumping, and we'll see all the blood in all the right places. We'll be able to see if there's anything actually wrong with your heart. I was fine, by the way. Turned out I hadn't had a heart attack. I had a caffeine overdose. I didn't know you could do that. Be careful. It sucks. So I finish my tests. I get done. He says, you're not allowed to take these drugs that are part of your medicines for the next 3 days, and don't go to the airport. Why can't I go to the airport? Oh, because the radiation detectors at the airport will think you're a bomb. Why 3 days? Because the change in the amount of radiation with respect to time is proportional to how much radioactive isotope I have in my body. It's the same freaking equation, except the K value here is negative. Sorry, is not negative. The K value is less than 1. The amount goes down. Matter of fact, we refer to how long it takes to go down by a specific name. The half-life is not just a game you play on the Xbox. The half-life of an element is the amount of time it takes to decay half of its radiation away. The half-life of technetium-99 is 6 hours. So after 6 hours after they gave me that shot, the amount of radiation in my body had already gone down by half. 6 hours after that, it had gone down by half again. 6 hours after that, by half again. 48 hours, that's eight. No, that's eight 6-hour periods. Half, 1 over 2 to the 8th. What's 1 over 2 to the 8th? We all have calculators. Don't do this in your head. It's really small. 72 hours, that's 12 half-lives, was barely noticeable. The amount of radiation left in my body was less than 1/10 of 1%. What was the number you came up with? 1 over 256. That's less than a half of a percent. 4 more periods go by. Divide that in half again and again and again. 256, 5, 12, 10, 24, 20, 48, 1 over 4,096. That's 0.0025, roughly. That's a very little amount of radiation. I don't smell like a bomb to the airport anymore. By the way, where's the technetium go? Right out the toilet. That's exactly right. I excrete it. My kidneys go into overdrive, and the rest of the element, the stuff that isn't radioactive anymore, gets caught up in my kidneys and filtered out. Every drug extraction metabolism idea follows this basic idea. You drink a cup of coffee, you drink your energy drink, right? You take in this caffeine. There's a spike. And then over time, your kidneys filter your blood and you excrete it out. So what happened to that monster you drank at 9 o'clock this morning? You peed it away sometime around 2:30. A single differential equation can model a whole lot of different objects. Not during class time. But one of the interesting things is that we have done exactly those studies. Every year there's a drug alcohol education thing that goes up on the wall outside of the Greensburg room in Low, right as you go around the dining hall. And it talks about how long does it take to metabolize a drink. If you drink one shot, 1 1/4 ounces of 40 proof alcohol, what is considered hard liquor, 40% alcohol, 80 proof. It takes roughly an hour for your kidneys to filter away all that alcohol. Roughly an hour. So if you have several drinks, from the time you start drinking, count out the hours. You have half a dozen beers in an evening, you're in trouble. For at least 6 hours, right? And what's problematic is that the amount of alcohol goes up and decays slowly rather than quickly. If we look at the solution to this, we'll actually be able to figure out what the graph of this answer looks like in another couple of classes. And we'll be able to see that it's fairly steep at the beginning and then it slows down. The alcohol curve goes the other way. The drug excretion curves go the other way. Metabolism, whole branch in medicine, if you go down to the PA groups and down to the LECOM people and to ask them about pharmacokinetics. Boy, doesn't that sound like a $3 word. Drug kinetics, drug changing, that's all they're talking about. Books about that thick. But it'll give you all the differential equations for each of the different kinds of metabolites. I can do the same thing with creatine powder. What's the excretion rate? How fast is it metabolized? Go through the whole same setup. Now, what rules am I going to use to construct those models? I'm going to go to chemistry class. I'm going to go to the organic people. I'm going to say, how long does this, how complicated is this molecule? What breaks it down? What metabolites are required to, I've forgotten the word, break it down. There's a word there. But all of these chemical reactions can be increased or decreased based on catalysts, right? Did you know alcohol? Did you know that drinking alcohol with carbonated beverages gets you drunker? Why?
I thought it could, but
Yeah, well, A, you drink it faster, right?
there's less oxygen. It's carbon
The carbon dioxide does something, but it's not that there's less oxygen, because that would affect my breathing. I'd be unhappy about that. It pushes the fluid in your stomach down into your intestines faster. Your intestines absorb more than your stomach does. So it gets to your intestines faster. Gets you drunker. And again, it fills up your intestines with the gas, right? So it's pushing all that out. It's pushing it against the blood vessels on the edge of your intestines. It's literally the physics of gas expansion. Burp more when you drink, it'll help. Drinking alcoholic beverages that contain sugar means that the drunk lasts longer. Why?
sugar.
Actually, it's the other way around. Your body likes sugar. It's going to eat it first. So what does that mean? It means it doesn't dissolve the alcohol first. The alcohol hangs around in your system longer. So those lovely fruity drinks, yeah, they have a hell of a hangover. They hold on to alcohol a lot longer. Same issue. As a matter of fact, it's almost the same differential equation. Heat. Black body radiation. Newton's law of cooling. The change in the temperature of an object is directly proportional to the difference between its temperature and the temperature of the outside. The change in the temperature of an object is proportional to the difference between its temperature and the temperature of the surroundings. This is why when you put an object into an oven, it starts to cook from the outside in, because that heat changes the outer layer, the difference changes there. You take that water bottle, nice and warm right now, go home and stick it in your freezer. It'll freeze, but not instantaneously, right? Because it's got to change the difference between its temperature and the surrounding. Crime shows. You get on NCIS or CSI or whatever, and you see the medical examiner, and he takes out this really long thermometer that's a metal stick, looks like the one you stick in an instant reader, and he sticks it into the person. What's he doing? Because your temperature right now should be around 37 degrees Celsius. What's it outside? 70-something degrees. Well, 70-something degrees is a little bit cooler than the 97, 98 degrees going on inside me. You come look at me in 6 hours, I'll have cooled off. By how much? The difference between me and the surroundings. As a matter of fact, whenever you listen to the medical examiners on these shows, oh, well, yes, last night it was fairly cold, so the temperature, and he does this, rattles off all this information. He is not solving the differential equation in his head. He's got a table he's looking stuff up on that he's done this for 20 years on. Matter of fact, Dr. Flowers downstairs has that very table. All three of these examples were in chapter 9 of the Calc book. You've seen them all before. And they're all the same damn differential equation. The only change between this one and that one is this extra number. So if I do a U substitution, U equals T minus the temperature of the surroundings, then the derivative du dt is the same as d capital T dt. It's the same damn equation. One equation, three different scenarios with the same actual model. Let's talk about spread of a disease. I can think of two different subsets in my group of people. And I can say, oh, I've got people that are sick, and I've got people that are not sick, that are healthy, unexposed to this disease. This could be the common cold. This could be malaria. This could be COVID. This could be anything. But now I can ask, how do these populations change? How does the number of people who are sick change?
Either more sick or morbidly healthy.
Right. But the only time people are going to get sick or healthy relates to whether or not they're already sick, or whether or not they're healthy and they meet someone who's sick, right?
Yeah.
So I would expect some sort of relationship that combines these two instead of just one. I would need some sort of joint proportion because the X person has to meet the Y person. Now, especially, we don't often do these as actual numbers. We do these as like fractions, right? So 1/10 of the population is sick and 9/10 of the population is healthy. That way, these numbers are less than one, and this multiplication makes sense. If I have 3 million people that are healthy and 23,000 that are sick, multiplying that doesn't mean shit. But if I think of them as proportions, that would make more sense. But then we could say, hey, well, these are the people who are, X are the people who are sick. So this is going to take healthy people and make them sick. We might also have some sick people who get healthy. That doesn't have anything to do with the healthy people changing, does it? This will take healthy people and make them sick. There's some chance every time they bump into each other. But there's also, hey, I got over my cold. I could also say, oh, we've got healthy people. They're going to change, aren't they? Again, I would expect there to be some relationship. Every person who was healthy that got sick is no longer in the healthy population. But I also would say it's quite possible for a healthy person just to catch a cold, right? You don't have to be exposed to someone else with a cold to get a cold. So there could be something else that just has to do with healthy people. Now, these are just my first guesses at what these equations should look like. And then I can go and I can survey the health center for what they did for the last cold season, and I can get some estimates on these numbers, K and L and M. And then I can wait for this year's cold season, and I start asking, am I close? Or is my model completely ass backwards and I screwed something up? But this is a system of differential equations. If we have a closed population, nobody from the outside comes in, nobody from the inside goes out, it's just this group of however many people, Well, then x plus y should be equal to 1 because that accounts for everybody. And then I could say that dx dt is negative dy. I'm sorry, I wrote dy dx. That should be dy dt. And if nobody was sick to start with and everybody's healthy, I could say y of 0 is 1, and then I have an initial condition. I have an initial value problem to work on. Let's think about the way in which chemicals decompose. We just talked about technetium-99 decaying, right? But I can also have chemicals that get combined. I'm not even going to bother with any sort of stoichiometry or actual molecular formulas or figuring out ratios. Let's just do 1-to-1. One molecule of A and one molecule of B combine, and I get a molecule of C. There you go. Okay, wait a minute. If this is what's going on, then I would say, how fast is the amount of chemical C changing? Every time I lose one molecule of A and one molecule of B, I'll gain one molecule of C, because that's how they get made, right? According to this equation. So the rate at which C is changing should be proportional to, I need a number for how much A I started with. I don't know what that is, but I make a molecule of C out of the A. I'm going to write up here that the concentration of A at time 0 is alpha. But I also need B, so I can say the concentration of B at time 0, let's call that beta. Notice what I'm going to end up with here. That concentration of C on the right-hand side is going to be squared if I multiply all that garbage out, right? This is a nonlinear differential equation. This is a second order equation. Sorry, a second order reaction in chemistry. The thermal class covers this rather thoroughly. I think so does Gen Chem 2. Talk about all those limiting reagents and stoichiometry. Last chemistry course I took was in a year that started with 198. It's been a long time. But notice that I am pulling ideas from every field I can come up with. Questions? I have a tank. Tank holds 300 gallons. And currently there is 50 pounds of salt dissolved in that tank. I then take a pipe and start pumping in pure water at 3 gallons a minute. But I don't want my tank to overflow, So I also let out the solution at 3 gallons per minute. I would like to know at any given time how much salt is in the tank. Now, I don't know how to solve this problem right now, but I think I can set it up. Let's build a model for what's going on. I'm going to use change. I want a differential equation. I'm going to use a derivative. I don't know much about the salt, but I know that the salt is changing. So let's look at dAdt. By definition, that is salt in minus salt out. Because that's what's happening in this tank that I am mixing up. Okay. At any given point in time, how much salt is going into my tank? Going in.
0.
Because over there it says pure water. So I know this is 0. What's coming out?
Some salt.
Some salt. Question. Salt is measured in, time is measured in, time is measured in minutes. Gallons is an intermediate here, isn't it? I don't know what gallons has to do with this yet. But I should be measuring pounds of salt in and pounds of salt out. So let's go back up here and see if we can figure out how much salt is coming out. At any given time, there's some amount of salt in the tank, right? And it's divided into all of those gallons. I can use my units. There's 300 gallons, and that contains A of T pounds. I've already screwed that up. LBS of salt. LBS, pounds is librum, from the scales we use to weigh things. The sign, Libra, is a set of scales. So LBS is Libra pundum, the weights on the scales. Weird you learn reading the history of math book. But wait a minute, that's pounds per gallon, not pounds per minute. How do I get that to pounds per minute? How fast is the stuff coming out? So I will multiply by 3 gallons per minute, and the gallon will cancel. I'll get pounds per minute. That works, and that's salt coming out. So it turns out I actually have a nice differential equation here. dAdt equals negative 3 over 300. That's 1 over 100 A of t. There's my differential equation. But wait, there's more. I have an initial value. There's a number over there in that picture I didn't use yet. The number up there I didn't use. There's 50 pounds of salt in that tank when I start, right? So there's actually an initial condition. So I actually have a differential equation with an initial value that I could now try and figure out how to solve. This happens to be a first order, first derivative only, linear, the only coefficient is a number, differential equation. Guess what? Chapter 9, section 5, calc 2, you solve this problem. Sum. But I like this kind of equation because the setup was just, well, I'm looking at one thing that's changing, the amount of salt in the tank. Now let's figure out how to write that expression. There is a discussion on draining a tank in the textbook. Torricelli. I think his first name begins with an E. E. Torricelli. The same guy who invented the barometer to measure air pressure came up with the mathematical idea of draining a tank through the bottom. And you think about it, if you're draining the tank from the bottom, the water goes out of the tank like it's falling. So you can treat it like it's gravity pulling down on the water. And then that's kinetic energy, therefore it relates to the height and the amount of push you'll get. So there's a discussion about gravity and the height of the tank and the size of the opening. And all Torricelli did to put it together was to figure out how much volume should be going through that hole. And his differential equation compares the size of the hole to the size of the area of the hole, the area of the tank, and the pressure exerted by the height of the water. The pacemaker company I did a summer internship from taught me a lot about electrical engineering. Circuits are all differential equations. My buddy Kirchhoff. I'm going to build you a circuit. This is a circuit with three components and a battery. E stands for electromotive force. That's my battery. It could also be being plugged into the wall, but that's alternating current, not direct current. I'm just going to go with direct current for the moment. We're going to use a battery. L stands for load. By the way, that twisty symbol is the filament of an incandescent light bulb. So that's the load. R is a resistor. It slows down the electricity so that we don't blow out the light bulb right away. C is a capacitor. The capacitor stores electricity up on one side, on one plate, until there's a lot of electricity and it jumps from one plate to the other. So if I'm pushing the electricity onto this plate, all of a sudden it goes boop and jumps over. A little spark happens. Most capacitors actually have some sort of material between those two plates that will raise or lower the amount of electricity needed to cause the jump. In some capacitors, you can spread those plates apart or bring them closer together manually. You do this in your car. You have intermittent windshield wipers, yes? You change how fast they're going by taking the capacitor that allows the electricity to make the motor move and spreading the capacitor apart. You do this with your fingertip too. The touch sensor on the screen of your phone is two parallel plates. When you push down on the screen, you're squeezing those plates close together, making it easier for the electricity in your finger to jump to the sensors on the screen. But it turns out, as the electricity is moving, that's called current. The charge is measured on the capacitor in quantity, so it's Q of T. Current is change in charge. It's how fast the charges move. Electricity goes running around my little circuit. That's current. Some of the current gets used up by the load. Some of it gets slowed down by the resistor, then it has to jump across the capacitor, but it's pushed by the battery. That's the force moving stuff. That's volts. Volts, amps, coulombs. They're all named after people. It drives me nuts. It turns out that the amount of voltage eaten up here and caused to jump here has to balance out perfectly. The amount of voltage lost through each of those pieces has to balance out with the amount of voltage we pushed through. And it turns out that Kirchhoff was able to quantify how much things push through. How much the load uses, that happens to be the second derivative, the derivative of my current. Resistance goes with current. Voltage equals current times resistance. V equals IR, physics 2. IR. Capacitance is inversely proportional. There's a lot of physics examples in the textbook. Suspended cables. All of these cables are plugged in, or I'd pick one up. If you hold something just by its ends that's flexible, it'll sag in the middle, right? If you hold it perfectly straight, that's one thing. If you let go, it starts to sag. You'll notice I have extra weight on mine. Take that off for a moment. Get off here. It sags in the middle. And depending on how far apart those are, that governs how much sag there is, right? How? I've got tension. I've got gravity pulling down on different pieces. I can work through how much force is being exerted on different parts of my cable in different places. And the change in position is based on the weight and the tension in the cable. Son of a bitch. Falling bodies. I know we did this one when I threw my keys, y'all jumped. Falling body, right? You go jumping out of an airplane, do you keep falling faster and faster and faster? Why not? I'm sorry? I'm not moving constantly. Gravity keeps accelerating me. What is that? It's terminal velocity. I'm going to die. It's terminal.
It's just like speed go.
There is a fastest rate at which a human body can fall. But what governs that? Well, it turns out that's air resistance. As I fall down, the air pushes up on me. I have to push my way through the air, right? So if I make a big star out of myself as I'm falling flat, I'm going to slow down. If I pull my arms and legs in, I'm going to fall faster. So my cross-sectional area, how much of me is hitting the wind, matters. How humid it is that day, how much water there is in the air, because water's thicker, slows me down. The temperature changes how much water the air can hold. Warmer air holds more water. I keep hearing this with all the global warming studies on hurricanes, right? Oh, crap. I got to work out air resistance to think about that. Terminal velocity means there's an asymptote somewhere in there. If I graph my velocity, there's some number I'm not going to get past. How do I find that asymptote? I'll have to solve my differential equation to figure out what things are proportional to the velocity, what things are proportionally acceleration. All of those pieces change. You see a car in a wind tunnel, that's what they're trying to figure out the drag coefficients and the shape of the front of the car and how it affects the moving through the wind.
So does a big person fall faster or slower?
Depends on what they look like when they're throwing themselves out the plane, does it? If I tuck my arms and legs in, I will fall faster than a skinny person. But if I spread myself out, I'll slow down. And I'll slow down more than that skinny person because I have a bigger area, even though I have more mass. Because drag is proportional to the square of the velocity, and gravity only pulls directly proportional to my mass. There's all sorts of neat physics coming here. So what do we do as we move forward? I'm going to look at 3 questions. Can I solve my differential equation? Can I solve it mathematically? If not, can I at least describe the solution? Terminal velocity, there should be an asymptote somewhere. Can I describe it even if I don't know exactly what it is? Qualitative descriptions. And can I approximate? Because if I can't get an exact analytic answer, at least let me get an approximate one. So there's analytic methods where I explicitly solve stuff using calculus. There's graphical methods where I can try and do stuff that's qualitative. And there's approximation methods where I can do numerical methods, like we do with numerical methods for integrating. And I can work out answers. The goal is to still turn the problem into something I can work. That means that this chapter, this set of homework is going to suck the hardest. We translate English to geek. Nothing but word problems here, people. All you have to do is figure out what's the important equation information I need under this. You should really look at a lot of these examples in this section. I know we got a 3-day weekend, so I don't want you to spend the entire weekend reading, but at least give me some look over before we come back on Tuesday, all right? I hope you all have a wonderful extended weekend. I will see you all on Tuesday.
Yeah, I think
That's important. I forgot to hit stop.